Hey guys, in this video we're going to talk about Chapter 9, Section 1, Sequences. So let's first define what a sequence is. Basically, a sequence is just an infinite set of numbers, a list of numbers, and the way we denote the numbers in the sequence are with the subscript. So the first term in the sequence is S sub 1. The second term in the sequence is S sub 2. And so on. And we call the nth term in the sequence S sub n. So that could be, any number we want. The 100th term is S sub 100, and so forth. So let's look at some examples of sequences. So the first example I have is this guy, 1, 4, 9, 16, 25. These 4 dots mean that we're going on forever with this list. So what's the pattern here? Well, we're squaring each number, right? Okay, so the sequence is S sub n equals n squared. And we can see this because let's look at the first term. The first term is 1. So S sub 1, if we plug in 1 into our little rule here, we get 1 squared, which is 1. Check. The second term should equal 4 when we plug it into the rule. So the second term is n sub 2. So wherever we see an n, we're going to put 2. And so we just have 2 squared, and that equals 4. And we can keep going. So what if I asked you, what is the 8th term in the sequence? What is the 8th term in the sequence? Well, this time n is equal to 8. So if n equals 8, the rule says that S sub 8, the 8th term in our sequence, is going to be n, which is 8, squared. So our 8th term is going to be 64. Now let's look at another one. So this example, we have 0, 1, 2, 3, 4. And this sequence is represented by the rule S sub n equals n minus 1. So we can verify this. So remember, this is the first term, second term, and so forth. Third term, fourth term in our list, fifth term, etc. So if we use the rule S sub 1, we're just plugging in 1 anywhere we see an n. So S sub 1 is 1 minus 1, and that's going to give us 0, right? That's what we have first in our list. S sub 2 is 2 minus 1, and that gives us 1, which is second on our list, and so forth. So what if I asked you, what is the 100th term in our sequence? What would that be? Well, here n is 100, that's the 100th term, and we just plug in 100 into our rule for n, so S sub 100 is 100 minus 1, which is 99. So 99 is the 100th term in our sequence here. Okay, so let's do some examples. Give the first 6 terms of the sequence. So here we're given a rule. Sometimes we write it with curly braces like this. And it's telling us that the rule is n times n plus 1 over 2, where n is where we're at in the list. So let's do this. The first term, the first 6 terms, so the first term is S sub 1. Well, if I plug in 1 anywhere I see an n, I just get 1 times 1 plus 1 over 2, and that's going to simplify down to just 1. So S sub 1 is 1. Now let's do S sub 2. We're just plugging in 2 for n, So 2 times 2 plus 1 over 2, and that's going to give us 3. And we can keep going like this. S sub 3 is 3 times 3 plus 1 over 2. And that's going to give us 6. S sub 4 is 4 times 4 plus 1 over 2. That's going to give us 10. Okay, so these are our first 6 terms in our sequence. 1, 3, 6, 10, 15, and 21. Let's do another example. Let's give the first 6 terms of this sequence. So S sub 1, this time the rule is n plus negative 1 to the n, all over n. So if we plug in 1 for n, we get 1 plus negative 1 to the 1, all over 1. Simplifying this, negative 1 to the 1 is just negative 1, so we get 1 plus negative 1, which is just 1 minus 1 over 1 is 0. All right, so S sub 2, we're going to get, this time n is 2, so we have 2 plus negative 1 squared all over 2. Negative 1 squared is just positive 1, negative 1 times negative 1. So this is 2 positive 1 over 2, and that's going to give us 3 over 2. All right, so we'll do the same thing for the next couple of terms. So 3 plus negative 1 to the 3 over 3. It's going to give us 2/3. I'm just going to kind of give you guys these last 2 answers just because it's getting a little bit repetitive. But anyway, these are the first 6 terms in our sequence. All right, what if we have to come up with a formula for the sequence? Well, we know that we have S sub n equals something, where that something should be in terms of n. Maybe I'll write that. Something in terms of n. So this is kind of like a guess and check sort of deal. What do you notice about the numbers, how they're progressing? We start at 1, then we go to 2, then 4, then 8. It looks like what we have here is powers of 2, right? So let me just copy this sequence down here so I can write under it. It looks like we have powers of 2. So this guy, we notice, is 2 to the 0. This guy is 2 to the 1st, 2 squared, and so forth. 2 to the 3rd, 2 to the 4th, 2 to the 5th. So the question is, how can I write this as a rule in terms of the position of the list, in terms of n? Well, I don't want to do, this is what I don't want to do. I don't want to do 2 to the n. Why is that? Well, because n is the position in the list. If I do S sub 1, that's going to tell me that the number in the first position should be 2 to the 1, which is 2. But that's not true. The number in the first position is actually 1. So instead of doing 2 to the n, let's do 2 to the n minus 1. Let's see if that works out. So if I plug in 1 in for n, I get 2 to the 1 minus 1, which is 2 to the 0, which is 1. That checks out. That's the number in the first position. What about the number in the second position. We should get 2 there, right? Well, if I plug in 2 into this formula right here for n, I get 2 to the 2 minus 1. That's just 2 to the first, which is 2. That checks out. What about the third one? Well, again, using my formula up here, I just plug in 3 for n, and I get 2 to the 3 minus 1. 2 squared is 4. That checks out. 4 is indeed in the third position. And, you know, it checks out all the way through. So let's just finish this off. So s sub 4 is 2 to the 4 minus 1, which is 8. That checks out. The number 8 is in the fourth position in our list. And let's do s sub 5. We have 2 to the 5 minus 1. That's 2 to the fourth, which is 16. 16 is indeed the fifth number in our list. And finally, the sixth number in our list should be 2 to the 6 minus 1, which indeed is 32. So that checks out. Okay, so we want to give a general form for the following sequence. So what I encourage you to do right now is pause the video and see if you can come up with a formula for the sequence. The first thing I notice is that the only weird fraction that doesn't look like the others in terms of the numerator is the 1/2. Right? All of the other numerators here have a 7. So I'm thinking here that my rule is going to have a fixed 7. And maybe this thing is going to be 7 over something that reduces, right? Specifically 7 over 14. So what's the bottom rule? Well, this kind of involves some guessing and checking here. What I'm noticing from one number to the next in the list is that the denominator is actually increasing by 3 every time. And so what I'm going to start with is a 3 times the position it's in, n, right? Because those are all going up by 3. And then I kind of just, I want to see what's happening when I plug in 1 for n, 2 for n, and so forth. So if I plug in 1 for n, first position is this guy. If I plug in 1 for n, I get 7 over 3 times 1, which is 7 over 3, which is not quite right. If I plug in 2 for n, then I get 7 over 3 times 2, which is 7 over 6, which is almost correct. Notice that the correct number is subtracted, you subtract 1 in both cases. So in this case, our formula is going to be 7 over 3n minus 1. And we can verify that all of these items in our list are going to show up in that fashion. So the first number in our list should be 7 over 2, right? If we plug in 1 into our formula that we just found, we get 7 over 3 times 1 minus 1, which indeed gives us 7 over 2. That checks out. S sub 2 is going to be 7 over 3 times second position, so n is 2, minus 1. That gives us 7 over 5. That checks out. Third position, we have 7 over 3 times 3 for the third position. That's n. And that's going to give us 7 over 8. That checks out. S sub 4 should give us 7 over 11. We get 7 over 3 times 4 minus 1. And indeed, we do get 7 over 11. S sub 5 should give us 1/2. So we have 7 over 3 times 5 minus 1, which is 7 over 14, which does reduce to 1/2. And finally, S sub 6 is 7 over 3 times 6 minus 1, so that's 7 over 17, and that does check out for our sixth position. Okay, so let's talk about another way we can define sequences, and that is recursively. So basically, recursive means that you're defining something in terms of things that came before it, okay? So these are not too hard to do. So let me just show you guys with an example. It says, give the first 6 terms of the recursively defined sequence S sub n equals S sub n minus 1 plus 3, and they tell us that S sub 1 is equal to 4. So basically, to find, like, we already have S sub 1. We have S sub 1 is equal to 4. The recursive thing is telling us that we have to use the S sub 1 to figure out the next term. And then once we get that, we use that to find the next term, and so forth. So S sub 2, if we're just plug in 2 into this rule here, we get S sub 2 is equal to S sub 2 minus 1. This is all in the subscript, all right here, plus 3. So S sub 2 is equal to S sub 1, right? 2 minus 1, that's going to be 1 in the subscript, plus 3. Well, we know what S sub 1 is. S sub 1 is equal to 4. So putting that back in the formula, S sub 2 is equal to 4 plus 3, which is 7. All right, so S sub 2 equals 7. You see how we found S sub 2 by using S sub 1 right here? And we can do that for S sub 3. Now S sub 3 is going to say, hey, put in S sub 2 and then add 3. That's what we're doing here. So let's find S sub 3. So S sub 3, according to our formula, is S sub 3 minus 1 plus 3. Now S sub 3 minus 1 is S sub 2, so I'll replace that here with S sub 2. And we know what S sub 2 is. We just found it. S sub 2 is 7. So this S sub 3 is 7 plus 3, which is 10. So S sub 3 is equal to 10. Now for S sub 4, you guessed it, we're going to use S sub 3. So S sub 4 is equal to S sub 4 minus 1 plus 3. Now S sub 4 minus 1, the subscript is just a 3. So this is S sub 3 plus 3. And S sub 3 we just found, it's 10. So this is 10 plus 3 is 13. S sub 5 is going to be S sub 5 minus 1 plus 3. Well, S sub 5 minus 1 is just S sub 4. And S sub 4 is 13. 13 and 3 makes 16. So S sub 5 is equal to 16. And you guys can verify this, that S sub 6 is going to equal 19. Okay, so that's how we found the first 6 numbers in our sequence that was recursively defined. Okay, let's do another example. Give the first 6 terms of the recursively defined sequence. So they tell us our first term is 2. So we know S sub 1 is 2. So our next job is to find S sub 2, the second number in our sequence. So S sub 2, I'm just plugging in 2 anywhere I see an n. So S sub 2 is negative 3 times S sub 2 minus 1. So this is all in the subscript right here. This is all in the subscript. Let's see. So maybe I'll write this a little bit better. S sub n minus 1 should be, that's an S. Okay. Well, actually, maybe, let's see. Let's write it like this. Maybe that's a little bit more clear. Okay. All right. So this becomes negative 3 times S, and in the subscript now we have 1, but S sub 1 is 2, so we can replace this with 2. Negative 3 times 2 is going to be negative 6. So S sub 2 is negative 6. Let's write it up here. Now we need to find S sub 3. So S sub 3 is going to be negative 3 times S of 3 minus 1, which is just s sub 2. So this is negative 3 times s sub 2, and s sub 2 we just found to be negative 6. So this is negative 3 times negative 6 is positive 18. So s sub 3 is positive 18. S sub 4 is negative 3 times s sub 4 minus 1. So this is just negative 3 times s sub 3, and s sub 3 we just found to be 18. Negative 3 times 18 is going to give us negative 54. So that's s sub 4, negative 54. S sub 5 is negative 3 times s to the 5 minus 1. So this is going to be negative 3 times s sub 4. S sub 4 we just found to be negative 54. So this is negative 3 times negative 54, which is 162. So s sub 5 is 162. And s sub 6, you guys can verify this, is going to be negative 486 when we plug in 6 in for n. Okay, let's do another example here. I am just going to do the first 4 terms instead of the first 6. So here is our sequence rule. They tell us the first 2 terms this time. They say s sub 1 is 0. The first one on our list is 0. The second one on our list is 1. So what's the third one on our list? Well, all we have to do to find the third one in our list is plug in 3 for n and simplify. So if I plug in 3 for n, I get 1/2 s sub in the subscript 3 minus 1 plus s sub 3 minus 2. Okay. Now let's rewrite this. So this is 1/2. This becomes a subscript of 2. So this is s sub 2 plus this becomes a subscript of 1, s sub 1. Now we know what s sub 1 and s sub 2 are, so we plug them in. So we have s sub 3 is 1/2 times 1 plus 0. So s sub 3 is just going to be 1/2 in this case. Okay. So s sub 4, I'm going to do the same thing. All I'm doing is plugging in 4 in for n into my rule that I have. So s sub 4 is going to be 1/2 times s sub in the subscript 4 minus 1 plus in the subscript 4 minus 2. Simplify this out. Now s sub 3 we know, and s sub 2 we know, and that's what we're plugging in right here and here. So s sub 4 is going to be 1/2 times 1/2 plus 1. So this is 1/2 times 3/2, which is just 3/4. So s sub 4 is equal to 3/4. All right, so these are going to be the first 4 terms of my list: 0, 1, 1/2, and 3/4. Okay, I'm going to do 4 again for this one. So give the first 4 terms of the recursively defined sequence. Okay, so here we are given the first guy, s sub 1. So s sub 1 is 1, so let's find the second number in our list. S sub 2, if we follow this formula and plug in 2 for n, we get s sub 2 is equal to 2 times s sub 2 minus 1. I'm just plugging in 2 anywhere I see an n. And this simplifies to 2 times s sub 1. Well, we know what s sub 1 is. S sub 1 is 1. So this is just 2 times 1, which is 2. Therefore, S sub 2 is equal to 2. Let's find S sub 3. So again, just using the formula, plugging in 3 anywhere I see an n. S sub 3 is 3 times S sub 3 minus 1 in the subscript. So this is 3 times S sub 2. We just found S sub 2. S sub 2 is 2. So we have 3 times 2 is going to give us 6. So S sub 3 is equal to 6. And let's do this last one, S sub 4. So S sub 4 is going to be 4 times S to the 4 minus 1. So that's equal to 4 times S sub 3, and we just found S sub 3 was 6. So 4 times 6 is 24. All right, so these are going to be the first 4 numbers in my list. So for this example, we want to actually give a formula for our sequence, and we want to define this formula recursively. So S sub n in terms of S sub n minus 1. So here I have S sub n is equal to S sub n minus 1, and then we want to kind of include some other stuff here. Okay, so what's the pattern here? Well, if I look from one number to the next, I'm noticing something. Here I go up by 2. From 3 to 7, I go up by 4. From 7 to 15, I go up by 8. And I go up by 16. And finally, I go up by 32. So the pattern here is that I'm going up by a power of 2 each time. So let's try S sub n plus 2 to the n. Is that going to work? Well, and let's say, S sub 1 is equal to 1, because that's the first term in our sequence. Is this formula going to work? Well, let's test it out. So let's test out with the second number in our list. We have S sub 2 is equal to S sub 2 minus 1 plus 2 to the 2. So that's going to give us S sub 1 plus 4, and S sub 1 is 1, so we have S sub 1, we have 1 plus 4 is going to give us 5, right? Not 3, which is what we wanted. So to fix that, I'm going to take off a power. Instead of 2 to the n, I'm going to do 2 to the n minus 1. So let's test this out. All right. So S sub 2 is going to be S sub 2 minus 1 plus 2 to the 2 minus 1. So this is just going to be S sub 1 plus 2 to the first. And S sub 1 is 1, so we have 1 plus 2 is going to give us 3. That checks out. And the reason it does is because 3 is the second number in our list, hence the 2 here. Okay, let's try S sub 3, see if that checks out. So S sub 3 is going to be 2 to the 3 minus 1 plus 2 to the 3 minus 1. So this becomes S sub 2 plus 2 squared. S sub 2 we just found was 3, so 3 plus 4 is going to give us 7. And that's true. 7 is the third number in our list. S sub 4 is going to be S sub 4 minus 1 plus 2 to the 4 minus 1. So that's S sub 3 plus 2 to the third. So that's going to give us 7 plus 8, which indeed is 15. It's the fourth number in our list. S sub 5 is S to the 5 minus 1 plus 2 to the 5 minus 1. So this is S sub 4 plus 2 to the fourth. So S sub 4 was 15. We have 15 plus 16 is going to give us 31. And that's true. That's the fifth number in our list when n is equal to 5. And finally, S sub 6 is equal to s sub 6 minus 1 plus 2 to the 6 minus 1. So this is s sub 5 plus 32, 2 to the 5th. And s sub 5 we just found to be 31. So 31 plus 32 is going to give us 63, which is right here. Okay, so this is going to be our recursive formula. Okay, so let's talk about convergence of sequences. We talked a little bit about convergence and divergence before, and we're going to bring it up again. So we say that a sequence has a limit if the sequence gets bigger and bigger, it approaches some number L. Okay, so L is going to be our limit. So if L exists, we say that the sequence converges to its limit, and if it doesn't exist, we say that it diverges. So basically, what this is saying is when we make n huge, right, so s sub, a very, very big number as n goes to infinity, we should approach a single number L. And that constitutes a convergent sequence. So, all right, so this is going to be something that we talked about in Calc 1, but I want to bring it up again just because you might use it for your homework. These are properties of limits. Okay, so basically, we've talked about these before, but here they are again. So you guys can see, you guys have used these a bunch of times before. The product property, the sum property, pulling the constant out of the limit, all of that stuff. So here's all the properties of limits and some other useful facts that we're going to be using here. The first useful fact is if we have a sequence s sub n equals x to the n, it converges if the absolute value of x is less than 1, and it diverges if the absolute value of x is bigger than 1. So for example, if we have s sub n equals 1 over 2 to the n, this is going to converge because the absolute value of 1/2 is less than 1, right? On the other hand, if we have 2 to the n, this is going to diverge, right? This is going to get really, really big without bound as n goes to infinity. And that's by the second part of the useful fact. Okay? So that's the first fact. And the second fact is something that we've used time and time again, in proving, in doing limit problems, really. The sequence s sub n equals 1 over n to the p converges to 0 if p is bigger than 0. Okay, so if we have something like s sub n is equal to 1 over, n to the 3, right? This thing is going to converge to 0. And we can see this with graphs too. If we go on Desmos and put in 1 over x to the 3, 1 over x to the 100, this thing is going to go to 0. So actually, let me get rid of some of this stuff. Let me show you what I mean here. So 1 over x to the 3, we can see that as n gets really big, this thing is going to go to 0. Same thing with, if we change the exponent, even if we just change the exponent to, let me see here. Even if we just change the exponent to 1, x to the 1, this thing is still going to converge to 0, as we can see here in the graph. Okay. So that was the second fact. Now let's talk about convergence and divergence. So does the sequence converge or diverge? If it converges, find its limit. Okay, so this is how we can write sequences in Desmos. Okay, so we start with a list. Okay, so let's say capital N. This is how we put our list in. This is basically telling us how many numbers are in our sequence, and we don't need an infinite amount of numbers. We just need to see what the pattern is. So we can do, let's just do 100. We can do 0, 1, 2, and then we can do ... 100. So this is telling, or it's 101 elements. This is telling Desmos I have 101 numbers in our sequence. Okay. The next thing is we want to actually define the sequence. So here, our sequence is S sub n equals 0.8 to the n. And I can just put that in here. So I have S sub n, or S of n, is equal to 0.8 to the n. And I'm going to uncheck that so that the graph doesn't show up. And the last part is I'm going to now create the points by inputting capital N, comma, S sub capital N as an ordered pair. So we have capital N, okay, the nth term in my sequence, and then S sub, or S of capital N. I keep saying sub when I mean of. All right, so now we can see our little sequence here. So we have 101 numbers plotted out. And hopefully you guys can see what's happening as the sequence, as little n gets bigger and bigger. What's going to happen is this thing is going to tend to 0. So in this case, it does converge, and it converges to 0. That's the limit. Let's look at another example. So does this sequence converge or diverge? Well, it appears if you were to put this in Desmos, just like this. Now I used 1,000 in this part, but it doesn't matter. I mean, you can use 100 too, as long as you have, you can see what the pattern is here. Okay, so here's my sequence is 1 minus e to the negative n over 1 plus e to the negative n. And it looks like this thing is going to converge to 1. Can we prove it? Well, yeah, we can prove it, because what are we really doing? We're taking the limit as this sequence gets huge, as n approaches infinity, of 1 minus e to the negative n over 1 plus e to the negative n. Now I can rewrite this. I can rewrite this as 1 minus 1 over e to the positive n, right, using exponent rules. Just changing this thing. Over 1 plus, again, using the rules of exponent, I can bring that negative n to the bottom. All right. Now, what's going to happen here is when I plug in infinity in for n, I get 1 minus 1 over e to the infinity, which is just infinity, over 1 plus 1 over e to the infinity, again, is infinity. And remember, guys, 1 over infinity goes to 0. And so we have 1 over 1. So yes, this converges to 1. This is the limit. Converges to the limit of 1. Okay. What about this sequence? Does this sequence converge or diverge? We have n squared plus 1 over n. Now, if we look at our graph, it's fairly obvious what's happening. As n gets bigger, well, the sequence gets bigger without bound, right? The output values, if you will. So let's look at this a little bit more closely, algebraically. We can simplify this thing, n squared over n. So we have n squared over n plus 1 over n. And n squared over n is simply n, right? So what happens, so here's our sequence just rewritten. What happens as we take the limit, as n goes to infinity, of n plus 1 over n? What happens? Well, when n gets huge, this thing goes to 0. And when n gets huge here, well, n just gets huge, right? When n is equal to 1 billion, n equals 1 billion. So basically, this thing gets large without bound. Without bound. So this sequence diverges. And we can see that from the picture. It's basically just a line, right? Okay, let's do another one. Does this sequence converge or diverge? Let's see. Well, let's just plug in a couple of different n values. So s sub 1 is 1 plus negative 1 to the 1, which is 0. S sub 2 equals 1 plus negative 1 squared equals 2. S sub 3 is 1 plus negative 1 to the third, and that again equals 0. S sub 4 equals 2, and the pattern continues. So we have 1 plus negative 1 to the fourth equals 2, and the pattern continues. So basically, we're oscillating between 0 and 2. So the question is, does this converge? Can we make n as large as we like and have this thing approach a fixed value? And the answer is no, because of this oscillation, right? If I say, as n goes to infinity, this thing goes to 0, well, that's not true, because I can find a number 1 greater than that will go to 2. You see what I mean? So this thing does not converge. So this thing, how about we be a little bit more, let's say this sequence diverges because it doesn't have a limit. Oops. It oscillates between 0 and 2 forever. Okay, so this thing is going to diverge. Let's talk about some definitions. We call a sequence bounded if there are numbers k and m such that the sequence is between these numbers for forever and ever, okay? So a fact is that if a sequence is convergent, then it is bounded. But the converse doesn't hold. So a bounded sequence is not necessarily convergent. Okay, so let's look at this first example. Here we have this example, the sequence s sub n is equal to 0.8n. This is bounded, right? And we could say that it's bounded below by 0, right? Because this thing is going to get super, super close to 0 as n gets large, right? It's tending towards the x-axis, but it's never going to actually equal 0, no matter how big n is. So that's what we say, it's bounded below by 0. It can never be 0, and it can never be lower than 0, certainly. So, okay, let's look at this one. A bounded sequence is not necessarily convergent. This was one of the examples we just talked about. 1 plus negative 1 to the n. Wait, was this one that we talked about? Yeah, we did. We just talked about that. 1 plus negative 1 to the n. So, yes, it is bounded. Why? Because the sequence never goes above 2 and it never goes below 0. So, bounded because the sequence never goes above 2 and never goes below 0, right? And that was the criteria for boundedness. The sequence has to be between two numbers. In this case, or in the second case, our number is always bigger than 2, always bigger than 0, but always less than 2. In this case right here, where it's bounded below by 0, let's write this out, just so you guys, I want to make sure you guys understand this. Here in this case, it's always, our k is always going to be 0, right? Right, it's going to be bounded below by 0. But the largest this thing is going to get is when n is equal to 1, which is 0.8. So that is what it's bounded above by. We can see the highest value is 0.8, and the lowest value is actually not going to include 0, but that is what it's bounded below by. So boundedness. Another definition that we need is monotone. So a sequence is called monotone if it's either increasing constantly as n gets bigger or decreasing. So let's look at some examples. So this first example is the sequence s sub n equals n squared plus 1 over n. So we can see from the picture, I mean, it's basically just a line with slope 1, but it's obviously different from a line because we're excluding the decimal values in our domain. Anyway, what I'm trying to say here is as n gets bigger, so does the function, right? There's never going to be like a weird, it gets bigger and then it goes like this, and then it goes like this, and then it goes like this. No, it's just going up and up and up and up. As n gets bigger, the output gets bigger. So this is monotone increasing. In a similar way, this function right here, 0.8 to the n, is always decreasing as n gets bigger. So we start at n equals 1, we're at 0.8, and the output is always going to be lower and lower and lower as we increase n. So that's monotone decreasing. This guy is not monotone. This old friend, s sub n equals 1 plus negative 1 to the n, and it's not monotone because from one value to the next, we're increasing, and then from the next one, we're decreasing, right? We're oscillating between 2 and 0 constantly. So when n is equal to 1, we have 0, then we have 2, then we have 0, then we have 2, 0, 2. So as n gets large, as n goes up, we're not increasing all the time, right? Because sometimes we go to 0. And similarly, we're not decreasing. So this is not monotone. Something that is monotone would be the natural numbers if we just listed them out. 1, 2, 3, 4, 5. This is monotone increasing. Okay, so we have a theorem. If a sequence is bounded and monotone, it converges. So let's consider this little sequence here. So this sequence is bounded above by m. We can see that, right? M is going to be our limiting value. So the idea is that, if this sequence is constantly increasing, aka monotone, then it's eventually going to pile up onto this limiting value, right? Because the limit it's keeping it there, right? It's never going to exceed the limit, right? Because that's what it means to be bounded. It can't exceed that value. And so the idea here is that as we approach that bounding value, that those points are going to pile up on that limiting value. And so that's, the relationship between convergence and being bounded and monotone. And that is all I got, you guys. I hope this video was helpful. Thanks for watching, and as usual, see you guys next time. Thanks.